All right, good evening. That's 7 o'clock, so we're going to kick off. I'm wondering if our Queensland attendees are going to wait another hour before they log on. So we'll just see what happens. Can I just get a quick sound check? Just let me know that you can see and hear me okay before we start. Just put your answer in the chat box on the right-hand side there, and I should be able to tell whether the sound's coming through. Have audio and vision. Thank you, Pat. Thank you very much. All right, so we're going to kick off because we've got a lot to get through in an hour. And if anyone jumps in along the way, that's fine. Like we always do, the file for tonight, the PDF version of this presentation, I'm sharing now, so you should be able to download that while we've got the preso going. If you've got slow internet, you can always wait till after the presentation's over and then just download it then. As always, if you have any questions, just throw the questions in the chat box on the way through and ask away. All right, so what we're looking at tonight is using the Drive Pro scan tool to activate a component and then using the PicoScope to do the testing on that component. So both of those tools are great tools for testing and diagnosing. When you use them separately, they're very, very good. When you use them together, they do work. They do work wonders. It's actually a very, very good diagnostic tool, or a combination of tools. It's very similar to being very, very adept with a multimeter and activating a component manually in the car, turning something on or revving the engine to change a value. But the great thing about the Drive Pro, we can pick an individual item to activate, whether it be an EGR solenoid or an EVAP solenoid or an engine mount, an electronic engine mount. We can actually operate that and then see the physical results with the PicoScope rather than looking at data or feedback, which is always modified voltage. So the idea of tonight, we're going to look at how we can test it, what patterns we should be seeing, and different ways of going about getting the information to do the testing. So actuations are a way of checking the physical operation of an output. Now, an output is a solenoid, a motor, or any electromechanical device. They're all our outputs. Our inputs are our sensors, the ones that pick up position sensors, rotating sensors, Hall-type magnetic sensors, pressure sensors. Anything that provides an input into the ECU, we call inputs. Controls or outputs are the actuators. So a fuel injector and ignition coil is an output or an actuator. Whenever we do a component activation using the scan tool, the component should click, buzz, move, operate, something should happen. So when we press that activate on the scan tool, something physically should happen. Now, a lot of the time it's okay to walk around to the front of the car, press activate and feel the throttle valve opening and closing. That's all right. It's better to see the valve opening and closing with your eyes. But what we often need to do is, because with a vacuum solenoid, we can hear it clicking, but we don't know if the valve is physically moving. So we may also need to do a vacuum test on it, where we put a Mighty Vac little pump on one side of the solenoid, we press activate, and when the solenoid valve opens, the vacuum level drops in our Mighty Vac tool. So that's another little test that we'll probably go through. But the best thing we can use is we also need to look at the signal from the ECU or the ECM. And the reason I say this is because we can look at a component and we can press activate on the tool, pick whichever output it is. If we press actuate or activate, and we're holding that component and it's not clicking, it's not buzzing, it's not moving, well, we have to think, well, do we condemn the component or do we do further testing? And the right answer should always be we need to do further testing, because what we need to know is, has that component got power? Has that component got ground? Is it sending a signal back? Is the component jammed? Is it a PWM control component? Is it a LIN bus control component? We need to make sure that the ECM or whatever control module is controlling that component is sending that driving signal up to the device. So that's the idea of the PicoScope. It will check the ECM's ability to deliver a control message to that actuator or to that component. And the PicoScope's great at displaying that in nice pictures. Okay, with any test we do, we have to have a reason for going there. So for this particular vehicle, I picked a absolutely brilliant car that always has faults in it. So I've used my Q7, and I tend to use my Q7 whenever I do training because it doesn't matter. Whenever I do a quick test, there are always faults in that Audi, and they'll be different every time. You know, if you ignore one fault for long enough, it goes away and a different one comes in. So I use that for this this training session, which is great because it has got faults in it. So the first thing we do, we need to know what the faults are. So we do a quick test. And it's quite simply plug the Drive Pro in, select Drive Pro, select European, select VAG because it's a Volkswagen Audi Group vehicle. And then we go and we do our automatic detection, and it's picked up the VIN, it's picked up the engine code, and then we just hit continue. All right, so once we're into the vehicle, this is the menu that comes up. The first button on our Drive Pro tool is always Quick Test, and it's generally there for this reason because that's the first test we should be doing every time. You know, we need to know what's going on with the car. So we run our quick test so we can actually produce a report. And the report gives us all of our DTCs along with freeze frame data that occurred when that DTC happened. So we've run this quick test report, and there it is. And if you've got your downloaded files ready to go, you'll be able to see that a little bit clearer. But basically we've got an intake manifold flap, airflow control valve, electrical fault, sporadic, so it was intermittent. And the second code, we've got intake manifold flap, position sender short to voltage, which is quite interesting. And as soon as I saw this, I was thinking, great, how much more money am I going to have to spend on this car? But it's good. It's great for training. You learn a lot working on Audis. So they're the two faults. So they're the two components we're going to test. And we're going to go through and do the activations to actually test that intake manifold runner solenoid. So that's where we're talking about a dual plenum manifold. So where we've got long paths and short paths, and the manifold just has a valve in the middle, and it just changes from that long to short path depending on whether we're looking for engine torque or whether we're looking just for outright engine power or wide open throttle. So we're going to have to activate this with the scoping to see why. We want to know why it logged that code. We want to know whether the signal's getting down to the manifold itself. So we have to go into IMRC actuation, which is intake manifold runner control. All right, so that's very simply from this same menu where we did our quick test, we come across to our drive unit, which is our engine control module. Then we select our engine electronics. Now in drive, we've got transmission as well here. We could do these same tests or similar tests on the transmission control. We could be operating some transmission control solenoids, just to check and see why it's not changing in a fourth gear or fifth gear or sixth gear. Okay, in this case, we're selecting engine control electronics, and then we hit next. So straight up when we're in engine electronics, we've got fault codes, module information. Dynamic requests in Audi is data. It's live data. It's data that's occurring, and they're all in measuring groups and the Volkswagen way. Then we've got actuations, control unit functions, and coding for this particular vehicle. So we click actuations, and then we have these, we've got 2 pages of engine actuations. Now, this is quite clever, this system, because I didn't realise there were so many output control devices on this Audi, and these are the ones we can test. These are the ones we've actually got capability of operating. Now, this particular car has active engine mounts. I didn't realise it had that. It also has an oil control valve solenoid or an oil pressure regulator valve solenoid. So the ECM can control the output oil pressure to the timing chain tensioner and other devices around the engine, which again, I think is a very, very clever system. And I didn't know the car had that. So we've got 2 pages on this particular vehicle. So we're actually going to look for intake manifold runner control, which is on our first page. Switchover valve. So these are all the ones we can test, and we'll test about 4 or 5 of these tonight. We're going to click on the IMRC because that's where our fault code was. So that's what we're doing. Right, so we've clicked on that, it then goes to another page. Right, so we click on that and we get ready to actuate. But there's no point activating the solenoid until we've got our oscilloscope attached. Now, with these particular cars, they've got valves and solenoids and actuators just mounted all over those engines. It's just an absolute mess. So sometimes I struggle knowing which valve is for what or which solenoid does what on the car, especially when you've got a bank of 3 or 4. So what I used here, which is also on the Drive Pro tool, is the AutoLogic guided data. So we'll just recap. We did our quick test report, which guided us to a fault in the IMRC. So we had a sporadic problem or a short to voltage problem. We had to locate the intake manifold runner control, and I did that using our AutoLogic data and just clicking on the location of that particular device. Now it's on the intake manifold. Now there were 2 motor control units there and 2 valve type units, and you can see there's actually 2 valves in there. It could have been this one or it could have been that one. Guided data told me it was this H5, which was great because that's what I have to test. So the next thing we need is a wiring diagram so we know which pins to probe. Now what we've done is we've located, if we go quickly back here, that's our diagram. That's obviously the pictorial diagram of the IMRC. We come back under the bonnet. Now that's somewhere at the front here in this bunch of mess. And if we just zoom in, we can see where our wires are. And I think we've got 5 or 6 wires in this harness. And it's one of those 5 or 6 that we're going to probe, or 2 of those 5 or 6 we're going to probe. Okay, so here's the circuit diagram that relates to this control unit. So it was H5. So this is using AutoLogic guided data. Again, H5 is highlighted. And what we've got labelled over here are what each of the numbers are, each of the terminals. So terminal 1 is the high side, so our high reference from the ECM for the switch or the position sensor. Terminal 3 is our low reference, that's the negative side. Terminal 2 is our position output. So that's our signal output there, number 2. So we're going to monitor that. We'll put a 1 trace or 1 scope lead into that number 2. We'll back probe that one. But we also want to make sure that the engine control unit is driving the electric motor over here. Now, we've got the high side driver on pin 5 and the low side control on pin 4. So the way these ones work, we've got 12 volt supply to one side of the motor all the time, and then we basically PWM or pulse width control the low side, the ground side. So that's the one we're going to go for. We're going to go for pin number 4 and pin number 2. So when we actuate it with the scan tool, we can actually see, one, that our motor is getting a signal, something's happening there, so we should see a signal, we should hear a noise, we should see a valve open. But I also like to look at the position sensor as well, just to make sure that that is feeding back to the ECM, to make sure there's no problem there. Now remember, when we use the scope to look at any data, we're looking at real data. We're looking at data that's actually happening at the actuator. We're not looking at modified data that we will see with the scan tool. So always keep that in the back of your mind. Any data you're looking at with the scan tool first has to go through this ECM where it's modified. It then goes to a gateway module where it's modified, it's changed over the bus. You will lose a little bit of information. If the system is good and it's working, 9 times out of 10, you do not have a problem. The data that's displayed at the scan tool is pretty accurate. This is just a little bit more accurate. And I have been caught where the data that I've been reading from the ECU is different to what's happening at the actuator. So when I do these tests now, I always use the scope. All right, so we know what we're going to probe on, pin 4 and pin 2. All right, so with our oscilloscope, we need a ground, and this particular ground, I'm using a black alligator clip, and that's just up on the negative jump post, which is in the passenger side of the engine bay, towards the rear of the engine bay. And here we are with terminals, back probe terminals, the pin terminals going to, I think it was number 2 and number 4. And I've color-coded them, so red is going to be channel B and blue will be channel A. So the next thing we have to do, once we've back probed, once the scope's connected, once we've got a ground on, we need to press Actuate on the scan tool. And the great thing is, that's all it is. That's your button on the Drive Pro, so it's pretty damn simple. Now, whenever Drive Pro actuates on this car, what it does, it turns the component on, then off, then on, then off, and it repeats it about a dozen times. And it leaves it on for a few seconds, turns it off for a few seconds. So basically, it doesn't just trigger it once. And I have had some scan tools that have done that, and it's a pain because by the time you've triggered it, you might not have recorded it on the scope, and it's a bit of dicking around. So the idea of the way the Drive Pro does this, it'll repeat the pattern, repeat the pattern, repeat the pattern, and it does it for every actuation. And you'll see that when we see the waveforms, you'll see the pattern that's very, very repetitive with the same time base. So here we go. We're going to press Actuate and go to our scope trace. So what I was using was Pico 7. I was using the new Pico software here. Again, it's not that much different to the old software. It's just it's a lighter version, probably a little bit faster. Definitely works on tablets very well. So let's have a quick look. The red channel was going to my intake manifold runner control motor. So that was going to the ground side. If you remember the circuit diagram, that was going down to the low side of the motor. Our pin number 2, which we've got plugged into the position sensor, so that's channel A. And we can actually see, as we've activated it, we can see our position sensor is coming up, it's staying on for a period of time, then it's turning off. Stays off for a period of time, turns on for a period of time, and then it stays on, then it turns off. Now you can see here where our electric motor signal is, we get this big pull down to ground. And what that's doing, the ECM is pulling that motor open and it leaves it there. And that's why we come down to ground. And then the next time it comes down to the ground, it pulls it closed again. Then it pulls it closed again. So what we should see, what we should feel, and what we should monitor on our waveforms is a very, very similar pattern. The position sensor is going up as the motor is being pulled open. And there it's happening again. The position sensor is going up as the motor is being pulled open. That's what we want to see. That's the pattern we should be looking for. Very simply, channel A, my time base is 5 volts because channel A is just a 5 volt signal. That high reference circuit, they're 5 volt signals. Channel B is 20 volts, and I have a 20 volt division because this is using 12 volts on the top side of the drive motor and ground on the low side of the drive motor. Now my time base here is a 5-second time base, and I've done that because it's a real-time sensor. So it's going open 5 seconds, closed 5 seconds, open 5 seconds, closed 5 seconds. And we can actually see that across the bottom here. So that's a good waveform. That everything that this car should have been doing, it was doing. There's absolutely no problem there. Why was it logging the fault? Not sure. So what we'll do is we'll zoom in a little bit. So here we are. This is our channel B. So this is my motor channel. Now at the moment, because I'm on a 5-second time base, I'm not seeing a lot of my low side driver out of the ECM. I'm not seeing a lot of that signal. So I have to decrease my time base or zoom in. So I'm going to change that back to, let's have a look at the next page. We've changed that back to 2 millisecond divisions. So rather than 5 seconds across the bottom here, we've got 2 milliseconds across those divisions. Again, voltage is exactly the same. Now, the reason we need 2 milliseconds because that is how fast the driver in the ECM is activating this electric motor. Now, if we have a look, we can see we're sitting up here at about 12 volts. So that high side there is our 12 volt supply. And when it pulls down low, that's the low side. That's the ECM grounding that circuit to pull the motor open. So you can see our on time between that point and that point is quite a lot more than our off time, which is that point to that point there. So this is driving the motor very, very slowly. Now, as our motor speed increases, the low side or the time that it's actually pulled down to ground will increase as well. So what we tend to look for here is just a nice square wave pattern, because what we want to see is that the driver or the transistor and the control module is doing its job, that the transistor is going open, closed, real square wave, real digital pattern. That's what we need to see across the bottom here. And we're getting that signal all the way. There's always a little bit of a spike at the top because, again, it's we've got current flowing through a conductor, so when we turn it off, we'll always get that little bit of back EMF. You'll see it's very similar to the back EMF we get from a fuel injector when we turn it off, just a little bit lower. So that's a good pattern. There's no reason that code should have come on other than the fact it was an Audi. All right, so let's move on to the next one. The EGR cooler switchover valve. So that's one we're going to test next. We didn't have a fault code for this, but because we're doing component activations, and this is another nice, easy one to get to, we'll do it. We'll have a look at it. So again, back in our actuation menu, come down here, EGR cooler switchover valve. Now, I had no idea where this was, again. So I'm going to use auto logic guided data. Just excuse me. Right, apologies for that. I needed to sneeze. Okay, so EGR cooler switchover valve. We don't know where it is, so we're going to use auto logic guided data again to find out. Here's our circuit diagram that's come up. So when we punch that into the guided data, it's told us here's the code for the solenoid valve, V8. Now it's just an electromechanical solenoid, and it's showing us it's a vacuum solenoid. So we could test this solenoid again by disconnecting one of those vacuum lines, putting our Mighty Vac on it, and applying vacuum pressure, and then using the hello Patrick, that's good. And then using the Drive Pro to activate it and watch our vacuum drop down every time it opens. So what I'm looking for here is the scope side. I want to see that the signal is getting to this solenoid and that we're getting the right feedback. So the fact that it's an electromechanical device or a solenoid, we should see some sort of square wave and some sort of back EMF every time. Number one is 12 volts. Number two is our low side driver, our low side control. Right, so this is the area this particular solenoid's in. I did use the guided data to find this, but I haven't put that page in here. And it actually hides right down under here where we were testing 5 minutes ago. So that's that plug we were testing at, and it's actually down here. So you can see the two wires, terminal 1 and terminal 2. If we go back to a circuit diagram, there's terminal 1, terminal 2. Now it doesn't look like it, but I am actually in terminal 2 here, the ground side. All right, so while we've got the scope in, let's press actuate and look at the waveform. This is much more exciting in real life, by the way. You're looking at photos at the moment, but when we do this for real in a classroom, whenever we're allowed to get back to that face-to-face training, it's definitely much cooler. All right, so with our scope, our setup, channel A, 20 volts. The reason I picked 20 volts is very simply, the circuit diagram is telling us there's 12 volt supply on this top side from this fuse. So we pick the 20 volt scale. All right, time base 5 seconds. The reason I'm using 5 seconds, again, is because it's a real-time measurement. We turn it on, we turn it off, we turn it on. This is the test that the AutoLogic tool does, the Drive Pro. So there's a 12 volt supply. So even though we are probed in with one probe on the drive side, whenever the driver is turned off, we're reading voltage through from the fuse down through the solenoid to where we're actually back probed, which is why we'll always see 12 volts there. And then when the driver in the ECM pulls it down to ground, we see the signal get pulled down to ground. Now we can see it's pulling down there. Now, while this is activating at the same time, make sure if you guys are doing it, just put your hand on the solenoid, make sure you can feel it clicking. Put your Mighty Vac in, apply vacuum to it, make sure you can see every time it clicks, we lose vacuum. But what we're checking here is the activation of the component. Now, here's our little back EMF. This is what I talked about before. So here's the solenoid turned off. As soon as we trigger it, it comes back on and we get this big back EMF spike. So we need to see that. If we're not getting a back EMF spike and we're just getting a square wave pattern, there's a good chance that the solenoid's not working properly or the solenoid's stuck, the solenoid's not moving. Think back to when we talk about fuel injectors, if we don't get that back EMF spike, we're not actually getting the pintle moving and collapsing back across itself. And the same sort of thing happens here. If we're only getting a square wave pattern, then we're getting a signal down, we're getting the driver signal, but we're not getting this mechanical movement inside there. So that's a nice, easy test. That's a good pattern. I don't know why we can't see the two drop-down lines there. They're definitely there. That's a great pattern. That solenoid's working fine. Okay, our next one. So this is quite interesting. Fan number 2 control circuit. So you would have seen back on our actuation page, we can control fan 1 or fan 2. This thing's got 2 dirty big fans like this on the radiator. Now, each of those fans has its own control module. And the control modules are fed with 4 wires. One of those wires is high current power, one is a high current ground, one wire is a ground for the computer, the little control module itself, and the other one is a LIN bus wire. Because the way these are controlled, these are a master-slave system. The ECM, the engine control unit, is the master unit, and the fan control motor is the slave unit. So it actually sends a signal via LIN down that particular wire. All right, here's our circuit diagram. So we are looking at E75 is our control module. So this is our fan control module, and E1 is our engine control unit. So we can see this wire that drops down to pin number 3 is our LIN control. So being LIN, local interconnect network, it's serial data. It should switch between 0 and 12, and we should see a really rapid fire 12 volt square wave pattern there coming on this one. If we're getting that signal down and the fan motor isn't working, well, obviously we're going to start looking at power supply from circuit 30 down through this fuse into terminal number 1. And this is a high current supply straight from the battery. That's a fuse battery wire. So pin number 4 is a ground. And if we follow pin number 4 back, we can see where it comes down to ground at this point here. E27 is fan control unit number 1. So they use a shared ground. And this other power wire is energized when the ECM turns the unit on. So ECM activates this power circuit down, and that powers up our LIN control. All right, so let's look at the next one. All right, so because we're testing an electric motor, I like to use a amp clamp, exactly the same way I would test a fuel pump. Now, looking at electric motors with an amp clamp is very cool because it actually tells you if the motor's moving. So anyone that's ever tested a fuel pump before and you've gone and checked with a voltmeter or a multimeter at the fuel pump connector under the back seat or under the back of the car, you'll plug in, you'll turn the key on or you'll crank it, and you should get 12 volts there when the ECM energizes the relay turns on, you should have 12 volts. That's great. It tells you you've got voltage to the pump. It doesn't tell you if the pump's actually working. So you can go through the trouble of disconnecting a fuel line, putting a flow gauge and pressure gauge in, connecting it all back up, then cranking, and seeing if you actually have flow or have pressure. That's also good. That test works fine. But I just find using the low amp clamp over the main current feed going to the electric motor works so much quicker. Because if I've got current flow, then that pump motor is turning. And in this case, I'm going to test a fan motor exactly the same way. Low amp clamp over the high current wire. If we look back here, that is going to be over this one. So terminal number 1, that's my high current. And then channel 1, I'm going to back probe into the LIN bus wire. And the LIN bus was terminal 3. So what I'm looking for here when I do my activation, I want to see that we've got LIN control. We want to see the LIN circuit or the LIN signal change from off to on. And then I want to see the current ramp up by using the amp clamp. And I want to see it reach, whatever the fuse on this circuit's rated at. So I can tell you that's if I clicked on that fuse, that would be a 25 amp fuse. So what I'd want to see out of this electric motor is somewhere around 15 amps peak is what I want to see. So sort of 2/3 of my maximum current flow. Okay, here we go. Press actuate, and go to the scope, and we'll see what happens. So our first page, I've turned off the amp clamp just to make this one a bit clearer. Plus, I've also had to zoom in a lot to see the LIN message. So when I use an amp clamp and I look at an electric motor, I'll probably look at a 5-second per division break in my time base because it's real time. The trouble with LIN is a very fast message. So I've got to increase my time base so it's faster so I can read more. So I come down to 500 milliseconds per division. So this is my LIN message. This is my fan command off. So as soon as I turn the key on, this is the message that goes down from the ECM to the fan control motor. And there it is. That is an off signal. And then as soon as I hit that actuate button and it powers up the fan, my message changes to that. That's fan command on. Now what happens, again, like I said, just like the solenoid where it turns the solenoid on, off, and the previous test, it does exactly the same thing with the fan motor. Powers it up, lets it spool up, turns it off, lets it spool down. And it's about 5 seconds that it leaves it on for. So what you see is if you looked at this whole trace, not just this one page, you'd see this off signal for 5 seconds, then you'd see this changeover, and you'd see the on signal for 5 seconds. If I have that message getting to my fan motor, guess what? ECM's doing its job. The problem's not in the fan motor. I can move on. Or it's not in the LIN circuit, I should say. All right, next page is my current flow. So this is the actual current flow through that low amp clamp. Now I've changed back to Pico 6 on this one just because it was a little bit more user-friendly for me. My scope settings here, so this is the channel B, the red one. I'm using the -5 to 20 amp clamp. That's the 60 amp clamp on the 20 amp mode. And my time base is now 5 seconds per division. The reason I split these two is because when I have them both on the one page, we can't see the LIN message because my time base has to be different. So over here, we can see our red line is sitting at 0 amps. That is when the fan is off or it's in standby mode. As soon as I press actuate and it powered that fan up, I go from 0 amps up to, I can't even read that, whatever that value is. And then it slows down a little bit and then it ramps up again. And this was my peak current flow here, and that must be around 16 amps. By the look at that, 15, 16 amps. So there's my 2/3 of that 25 amp fuse. It stays on for about 5 seconds, and you can see here, because I'm on a 5 second base, I've got 5 seconds between there and there. So that's my on time. 1, 2, 3, 4, 5, and then the motor slows down and it turns off. That's what I need to see. So by doing a simple test, now I might not be able to see the fan. In this case, it's an electric fan. You're going to hear it. You're going to see it. If it works, it works. What you might be doing this test for, the fan might be spinning slowly. It might not be reaching full speed. So what you're doing this test for is, one, to make sure that your LIN message is getting through properly. The correct LIN message is getting through to the fan control motor. You're also going to look at your powers and grounds on that fan motor. But you want to do this test to make sure that it's drawing the right current. It might not be reaching full speed because it's just simply not drawing enough current, which means we might have a resistance problem somewhere. And the other thing we can do, we can zoom right in on this pattern and look at the individual commutator segments on the motor, just to see if the motor itself is breaking down. All right, so that's what I'd expect to see for that one. All right, our next output control that we're going to look at is the throttle valve control circuit. Now, yes, this is a diesel, but it still has a throttle control motor. And we use the throttle valve on a diesel for a couple of different things. We use it when we turn the engine off. So when we turn the key off, we not only stop the fuel, but on all diesels now, we shut the throttle valve completely to cut the air off. And the reason we do that, it prevents the engines from running away in case they get a bit breathy or they start drawing a bit of oil in from blow-by gases that goes up past the turbocharger, or even oil coming down past the injector seals. So we are shutting the fuel off most definitely, but by shutting the air off as well, we're guaranteeing that engine's going to stop. The other reason we have a throttle valve on our diesels is for blending air with EGR. So when we operate the EGR valve, or when the ECM decides to operate the EGR valve, it draws exhaust gases easier from the exhaust manifold if I can shut off some of the intake air. Because remember, engines are lazy, they'll pick air from the easiest point, a bit like electricity. And if the throttle valve is wide open, the airflow will come in there and it'll take a lot more air from there down into the intake than it rather would drag exhaust gases out. But by restricting the intake flow of air, as the piston drops down, it's got to draw air from somewhere, or it's got to draw gas from somewhere to fill the chamber. So it's more than likely to pull it out of the exhaust system through the EGR. So that's what we use the throttle valve for on diesels. So here we go. We want to go to the throttle valve. So in this particular instance, it's on the next page. We hit next, and there it is there, and we click on that one, get it ready to go. Next page. Again, we need a circuit diagram because I'm not a Volkswagen person, so I don't know where all the wires are. So here we go. H4 this time is the one we want. H5 is what we tested before. We're now testing H4. This is our throttle valve. And it's wired up exactly the same way as that valve. We've got a position sensor here, high reference, low reference, and signal out. And over here, we've got an electric motor with the voltage in and the voltage out. Now, just be aware that some of these throttle valve motors do change a little bit. They might not be a positive side on the top or a negative side on the bottom. They might have what we call a bidirectional driver on both sides. And what that means is we can change the feed in from negative to positive or positive to negative. And what that means is we can push the motor, push the valve open using electricity, or we can pull it closed using electricity. Most petrol engines are like that these days. The electronic throttle control on most engines use bidirectional drivers. So just keep that in the back of your head. All right, here we go. These are our connections. So again, we're going to look at probably the signal output here and our low side control there. Now, being that it's a throttle valve, it's wired exactly the same as our IMRC motor, we really should see a very, very similar pattern. So let's have a look. Let's find where it is. There's our throttle valve over here. Here's my connector. This is actually a little bit hard to get to. It's way over the back and underneath there. But I managed to get the connector in the back probe. So this is our first terminal we've plugged into, and we'll put another one in there for our position sensor. All right, here we go. Press actuate, and let's go to our trace. So what we're seeing straight away is now we're on a 5 second per division time base across here, and I'm using 20 volts on one side and I'm using 5 volts on the other. Now this is very similar to the other one, where it was only turning on for a very brief amount of time. We're actually pulsing this quite a lot. So we're operating this really, really quick to wind that motor open and then wind the motor closed. So when we look at our position sensor, we can see that we're closed, closed, closed here for 5 seconds, snap open. Now we're open for 5 seconds. Now you can see that change between open and closed in my position sensor here corresponds with the gap in the electric motor there. So we're driving it closed in this case, then we're driving it open. Drive it closed, drive it open. Now I can't really see my electric motor signal. I can't see the driver's control to that motor very well. So I'm just going to zoom in on that on the next slide. And here it is here. So my time base has changed to 2 milliseconds per division rather than 5 milliseconds, but my voltage is still the same. And you can see I'm going from 0 to 12 volts because that's what the circuit voltage was in this car. So you can see the square wave pattern. We can see that we've got 12 volts applied, we pull it down to ground for a very short period of time. 12 volts applied, pull it down to ground. It's a square wave pattern, it's an electric motor, it's not a solenoid, so we're not getting that spike that we do on solenoids. That's a good pattern. That's what we should be seeing on any one of these type driver devices. If that was flatlined down here at 0, we'd simply say that we've got open circuit in the control wire, or there is no driver. The transistor inside the ECM has failed. It's gone open, or it's just not operating. If we saw that stuck up at 12 all the time and we're testing on that low side, that would be a short to voltage. So you really do need the circuit diagrams to know what you should be looking for on these waveforms. All right, very quickly, on to the next one, fuel pump electronics. So let's have a look at this. So let's go into actuations for that. There's our fuel pump electronics. Now this is actually a very cool function on this car. So what the fuel pump electronics actuation does, it just turns the low pressure pump on in the tank. Now the low pressure pump on these diesels operates around, I think, 50 to 60 psi pressure. So it's kind of in the range of multi-point fuel injected or even GDI in tank pumps. So we can treat it exactly the same as we would a petrol vehicle. Now, the good thing about having an actuation on our fuel pump, especially on a diesel vehicle, think when you're servicing the car, think when you change the fuel filters and you've got to prime the system back up. If you get a lot of air in, let's say it's Colorado and you've got two dirty big fuel filters underneath. Now with the Colorados, I know you've got to sit there and crank the engine, turn it off, crank it, turn it off, crank it, turn it off to prime the system to bleed all the air out of the filters. Well, with the European stuff, sometimes it's a little bit harder. So having this activation button on the tool means that once we replace our filters or replace our fuel line or whatever we happen to be doing, we can actually prime the system and self-bleed it by activating like that before we even crank the engine. And that saves a lot of heartache of misfiring and rough running engines and noise and that panic you get when the car doesn't run properly, especially a Euro vehicle. So that's what that's also handy for. But in this instance, we're going to test it because, we might have had a problem with the fuel pump. Maybe the car doesn't start. Maybe it doesn't start. And I want to go, well, is the fuel pump actually working? And this is a good way to do it. So there we go. Go to next. So for this particular vehicle, I was thinking, right, I'm going to put my my low amp clamp, my 60 amp low amp clamp, I'm going to put it on the feed wire to the fuel tank, to the fuel pump. And I thought that'll be awesome because it'll just be under the back seat. It's not under the back seat on this car. It's a two-part fuel tank. That's actually under the car. You've got to lower the fuel tank down to get to that. To lower this down, basically the rear cross member has to come out, the rear final drive has to come out, the tail shaft has to come out. And for the purpose of doing this webinar, there was no way in hell I was going to do that. So I found that out simply by going again to the guided data and looking at the location of it. I went, you know what, that's too hard. So there was another way to do this. I went to the fuse. Now, again, guided data told me where the fuse box was for that. So it's up here on the left side of the engine bay somewhere. It told me it's a 25 amp fuse where it's located, and it gave me the location of it just there. That made life a lot easier because if I can test the fuel pump fuse for current using the scope, it saves me a whole lot of time. And here's how we did it. So that fuse box lives up over here, somewhere beside the fuel filter that we just replaced. And what I'm using here, once I've popped the top off the fuse box, I'm putting the fuse piggyback wire. And if you haven't seen those, they're the best invention really since, the inflatable wheel. They're great. You pull the fuse out, you put this piggyback in, the piggyback's got a loop on it, a loop of wire on it, and then we put our original fuse back into this fuse holder on the side of that loop. That loop allows us to put our amp clamp over the top and read all the current flow through that wire. Now, this being the fuel pump fuse, every bit of current that powers that fuel pump, I can now read. And I'll read it exactly the same way that we did the fan control motor. And that's what we're going to do here. So we're going to actuate it, and we're going to look at the waveform. And there it is. So this is really interesting. Again, I've got a 5 second per division because it primes it for 5, turns it off for 5, primes it for 5, turns it off for 5. And that's what we're seeing here. When this voltage goes from 0 to high, we have pump on, then we have pump off down at this 5 second interval down here. Now, you're all going to ask me, and I know it now, you're going to ask me, what's this spike here? Is that back EMF? No, it's not. Because this is not a solenoid, this is an electric motor. But what you are seeing on this particular fuel pump is the initial breakaway current that pump needs to get spinning. So for any auto elects that are out there and listening, you often look at breakaway current when we first crank the engine, and that's the massive amount of inrush current from the battery to the starter motor that we see to get the starter motor turning, to break the friction of the crankshaft bearings through the oil and get the crankshaft turning. Once the crankshaft's actually turning, we see that current drop back down. That's exactly what we're seeing on this particular device here, because we're looking at amps, right? We're not looking at voltage. So we're seeing this big spike of current through to get that pump to turn, and then it drops back down pretty quickly. Now remember, this is a 5-second division. There's 5 seconds across there. So that's probably turned on. That peaks up for about half a second before it comes back down. And that peak is in the vicinity of, that's 20 amp maximum. So that's in the vicinity of 19 amps that circuit's drawing. So these things do draw a lot of current to get them going, but it's only on for that short period of time. When it's actually running, we're back down here around looks like the 9 amp or 7.5 amp level. And that's pretty right for what we're looking at on the low pressure side of the diesel. That's probably a little bit higher than what we'd see on a petrol. We probably only see around 5 amps on a petrol. But remember, your diesel is a little bit thicker. It's a little bit more viscous. So the current draw will be that little bit higher. What else do we see there? The image is a little bit bad, but that does close off. So the fact that I'm seeing a square wave on and off here, that's telling me the control module is turning it on and off. The fact I'm looking at current and I can actually see the current flow through the device tells me that pump's working. Now, like a lot of cars, when that fuel pump starts, you can't hear them. So you don't know if it is actually working unless you've got a fuel pressure gauge on. I like to do this because it's a whole lot easier than connecting a mechanical fuel pressure gauge. It's very, very quick. And once you've done it a few times, you start to learn what you should be looking for, and you have more confidence in looking at the waveforms versus an analog gauge. So again, here you can see the settings that I've got this on. Now what I've done on this one, exactly the same settings, except I've changed my time base down to 20 milliseconds per division. And you can see here we're drawing around the same current flow. So that's probably just the top of one of these that we've zoomed in, we've had a bit of a look at. Now, what I'm looking at here, see all these highs and lows, these troughs? Well, because I've zoomed in and I'm looking at current, what we're actually seeing is the commutator shaft segments. As each of the segments draws current through the commutator and then into the armature of the electric motor, it draws the current increases. And then when the commutator rolls past, or the armature rolls past the brush, we can see that the current drops back off again. So we do tend to look at this a lot with starter motors because the starter motors tend to turn over fairly slowly. We can see it very well. Fuel pumps are exactly the same. We can start to see problems in our fuel pump before they occur. And what I mean by that is the reason a lot of fuel pumps fail is it's not so much because of, well, it is, they do fail because of dirt, gunk, water, the connectors on the ends burning. But basically, they're a brushed DC motor. They wear out. Those brushes wear out. You can't do a visual inspection on them. So a good way to look at it is look at the segments using your amp clamp. And you can start to tell whether a fuel pump's going to fail. We did one in New Zealand as a test, and we could actually see it. Every second rotation, it dropped 2 of the segments in the commutator, and then it had come back, or 2 of the segments where the commutator went past the brush. And what it appeared to be was that as it was rotating around, the brush was just worn that much on that particular section that it would just glide over the top of the commutator and not actually transmit any current. And that's where we'd see this drop down to 0. So using this method of activation and follow-up with the scope, that's a good way to look at problems before they occur. And I'm not saying do this with every customer, but you might be looking at cars that may have a high instance of failing in a fuel pump. And at least you can give the customer a bit of an idea what's going on. Okay, so now we're going to have a look at the EGR vacuum regulator solenoid valve. Yay, there's a mouthful. So here it is here, the EGR vacuum regulator solenoid. So this is the one, that's the cooler. This is the one that opens and controls the EGR valve on this particular car. And the reason I wanted to leave the EGR valve to a little bit later is because they're problems for us. The number of EGRs that I see that fail just in my travels, and I'm not full-time in the workshop, so I can only imagine how many come through your doors. with problems, gummed up, sticking, not working, shorted, who knows. I know they're a big issue. So we need to know how to test it, and a great way, activate it, have vacuum on one side, have the scope on it as well. Let's have a look and see whether we're getting a signal from the ECM. Let's see if the vacuum is moving. Let's see if it's clicking. Let's see if the electric motor is moving. So here we go. We're going to select that one. We need the circuit diagram. Here it is here. So this is a vacuum type. Again, it just shows a solenoid motor with a feedback position switch. And what we've got here, high reference, the solenoid low side control, low reference and signal. So this circuit over here is our position switch. Now you probably notice that all the position switches we've seen tonight are all exactly the same, regardless of where they are. Now, it doesn't matter if this is an Audi, it could be a Mitsubishi, it could be a Mini, it really doesn't matter. The position switch is going to be identical in operation because that's how electronics work. 99% of them use a 5-volt high reference. The rest, they have to have a ground. The signal return is always labelled like that. The signal return is going to be somewhere between 0.5 volt and 4.5 volts on every one. Once you know that, it makes testing a lot easier. And this is a solenoid, so obviously we should see high side here, 12 volts in, low side out. So we test terminal number 2. Yep, there it is there. And we're going to activate it, and we should see a square wave pattern, and being a solenoid, a bit of back EMF because we're looking at voltage. Right, this is the general location of this solenoid. There it is there, nice easy one to get to. I'm back probed into pin 2. I'm not in the position switch, which is down on the side. All I'm looking for is the driver signal. Okay, actuate, here we go. Let's see what we get. And nothing. So this is my car. This is actually happening on my car. So I went back and I pressed it again. There was nothing. I held the vacuum solenoid. No clicking, absolutely nothing. I put my Mighty Vac on it. Wasn't operating. So when I saw this voltage sitting at 0, and I've got that in, here we go, let's go back, back. And I've got that into pin 2. From all the stuff you've seen tonight, you should be seeing a square wave pattern because that's what should be happening. Now, I can tell you now the tool's not broken. The tool's working fine. This is the actual output value on this car. So this is where we go. So remember, we're looking at a vacuum solenoid because we've done a quick test. The quick test has led us to a problem in here. And it might be that position sensor is out of range. It might be that the feedback voltage from here is sporadic or not working. But you've come to this point and you've actually found that there's no voltage. So this is where you've got to do further testing. Now, in this instance, because of my test location, which is here at the solenoid itself, I then need to move my probe. So I'm down here at the solenoid. I then need to move my probe back up here to the ECM, back probe there, and see if I get the square wave coming out of the ECM. If my square wave is there, if it shows up, then I've simply got an open circuit on that wire. Problem solved. Fix the open circuit, job done. If I have no signal when I back probe there, well, I probably need to pop that connector off and have a bit of a look at the terminal, make sure the terminal's not spread, make sure it's not an open circuit problem there. In this particular instance, the engine control module, whoops, let's get the picture of it, I'll just go the right way. The control module on this car sits just up under this little plastic flap there. It's very, very easy to get to. And I did this the other night, and I just simply moved that from there back up to that number 44 and just back probed it in. And I did the same activation test. And we had exactly the same result. We had 0 volts coming out of the ECM. So my EGR is not working. Is that a good thing? Yes, it is. Because a few years ago when this car was purchased, it had an issue with the EGR valve, and it had a modification done to it back then, not done by us, and I don't condone this, but it had a modification done to turn the EGR system off. I didn't know about that until I did this test the other night. So once I did this test, I went, oh, geez, there's something wrong here. I started thinking about the history of the car, and I rang up the previous workshop that did some work on it, and they went, yeah, this is what actually happened. So there's always a reason for what we see here, and that's what's happening. The EGR is activated, but the voltage is sitting down 0. So in this case, on this vehicle, it's a good thing. The EGR valve's not being opened. But if you're presented with a problem where a DTC comes up in your quick test report, leads you to perform an activation, you can see an activation is very easy, very quick to do. You can see that all those solenoids have a very, very similar pattern. It's real-time activation, set it at 5 milliseconds per division, and your voltage will generally always be 12. Electric motors are a little bit different. But the testing by using component activation is very quick and very easy, and it tells you pretty much what's going on. In this case, when I first saw it, I thought open circuit. There's a problem between the two. Because I've got the circuit diagram handy on the same tool, it was just simply unplug, plug, test. Right, it's not an open circuit. What is it from here? So you can see where having the information available, having the test parameters available, and actually being able to see what happens can guide you the next step of diagnosis. Really connect the dots, 1, 2, 3, and the problem solved. And that's it. That's it for component activations. There was a whole lot more in there we could have done, but at the end of the day, you would have noticed for the 4 or 5 solenoids we checked, they were all exactly the same. And I could have gone through and tested those engine mount solenoids. I could have checked the oil pressure control solenoid. The result would have been the same. Same square wave pattern on for 5 seconds, off for 5 seconds. Same little back EMF spike. Once you see how one solenoid works, they're all identical. A fuel injector is a solenoid, works exactly the same. So as long as you've got the ability to drive the component and a scope to look at what's going on, you can tell exactly whether that component's working or not, or the control signal from the ECM is getting there. And that is the end of our session, and I've gone in under time at 7:56. First time ever I've come in under the hour. All right, so if you have any questions, flick them through in the chat box. Either everyone went to sleep, or no one had any questions, or you all went off and got a cup of coffee. Oh, I had a cup of coffee and I let it get cold in front of me. It's cold. Yep, no worries, Pat. I hope you all got something out of that, even if it was one really, really small bit of information, because anything in the diagnostic arsenal definitely helps. So like I said, this presentation is in the file section. Download it, save it, have a look at it, use it as a reference. If you have any questions on anything we've done tonight, please hang around and ask. Send me an email, give us a call. I think I've given my phone number out a few times. If there's anything AutoLogic can help you with, drop us a line via the website. Like we have been doing, there is a webinar on every Wednesday from now until Christmas. So if you are bored, 7 o'clock this time, I do my webinars. The BMW, Volkswagen, JLR guys, they do theirs at 2 p.m. in the afternoon because they're absolutely worn out by the time they get home. They don't want to be doing this at night. And because I'm only a very relaxed worker, 7 o'clock suits me. So yeah, tune in, register via the website. I'm going to turn the camera off. I'll keep the chat box open. Just flick your messages through. Hope you have a great night.